So we've seen stress concentrations in axial load, we've seen stress concentrations under torsion, and this is going to be no different. We're going to round out our beams and bending section here with talking about stress concentrations in bending. And much like in torsion or under axial load, these stress concentrations happen when we have changes in our cross-sectional area, right? Changes in our geometry. And for bending, usually the changes we're looking at are when we have notches. So maybe some kind of little notch in there. We might also see holes. A hole in our thing that we're bending, right? It's being subjected to bending. Or just as we've seen in our other ones, we could have just a lowering of the cross-sectional area, so going from a wider to a smaller section, usually with shoulders or fillets like this. But these are the typical cases where we see these changes in cross-sectional area that cause these stress concentrations. Now, for bending, our stress concentration equation looks a little different. Our stress concentration equation is actually going to be our bending stress equation, just with the stress concentration factor K out front. It's included in our equation now, mc over moment of inertia. That's our main difference here. We just go ahead and include this in the equation when we're calculating our bending stress. So it does come with another handy dandy table. Right, we've got a slew of tables depending on what kind of notch or hole you're dealing with. This one we have a filleted connection, and then our table below here we have some notches. So just depending on what scenario you're looking at, we can look at different tables to determine our maximum stress using the stress concentration factor to kind of reduce the amount of stress so that we're kind of reducing the amount of risk we're taking on, right? We want to lower our allowable stress so that we don't overstress it at these very delicate sections. So let's take a look at an example. So this example asks us to find the max normal stress developed in a bar with a given yield stress of 500 megapascals and a moment of 5 kilonewton meters. And we're given this funky shape over here that's just a little bar that is filleted here with a radius of 16 millimeters. So since we know we're dealing with this funky shape that's undergoing this fillet, we know we're going to have to use our stress concentration to reduce the amount of acceptable stress here. So we know our stress concentration equation, or the way we're going to factor it in for a bending moment, is K times moment Y over I. So first thing we'll do is we'll find that stress concentration factor. That's usually our easiest way to start these problems, and then we'll gather all the ingredients before we go cook this up in the kitchen. So our stress concentration factor for a filleted guy like this uses this table here. Right, it shows us our filleted connection there. And we're going to need to pull two values. We can see our x-axis is r over h. And then our line is going to be w over h. So h is the height of the skinnier portion, W is the height of the wider portion, and then R is the radius of that fillet. So I need W over H and R over H. So for my shape here, R over H, our radius of our fillet is 16, and the height of the skinny portion is 80. So I can plug that into my calculator to get that ratio of 0.2. And then I needed my W over H, so the wider portion is 120 millimeters over the skinnier portion is 80 millimeters, and that gives me 1.5. You notice I don't convert the units for these. Since these are just ratios and all my units cancel anyways, I don't bother with converting these into meters. It's going to work out the exact same if you do or if you don't. Doesn't really matter even a little bit. So it's up to you if you want to convert them or not. I don't, since I just want to grab these ratios real quick. So my ratios are 0.2 and 1.5. I come back over here, 0.2 on my x-axis, right here, and my W over H was 1.5, which is the middle line. It's the lightest line out of these 5 lines. So I'm going to follow my 0.02 up until I hit that lightest line, which looks like it's right here, that middle line. And then I bring my cursor over to the left to see what that value is. And that K value is 1.45. That K value there. Oops. Alright, I guess that box is just there now. Thanks, Windows. 1.45. Alright. So I have my K value. I just need to grab all of these other values. They gave me a yield stress. They gave me a moment. They gave me a moment of inertia. So I'm going to find my Y value. Right, my moment, they gave me 5,000 Newton meters. My Y value is just that distance from the center to the outer edge, and that's going to be for our smaller one, right? Our smaller section here. The distance from the centroid to the outer edge is going to be 40 millimeters, right? The centroid happens right in the center there. So 40 millimeters or 0.04 meters. And then my moment of inertia is, this is a rectangular cross-sectional shape. So I only need to do the 1/12 base times height for that smaller section, right? The smaller section is the limiting section, so that's the section that I want to use. 1/12. My base, my thickness here is 20 millimeters. And the height is that 80. 0.08 cubed. So the moment of inertia is 8.5 times 10 to the -7th meters to the 4th. And again, I like to just convert everything as I'm going, so that when I actually get to my equation here, right, I'm finding the max normal stress. All I need to do is plug it in. And I might do this in a different color so I can see it better. 1.45 times that moment of 5,000. Oh, I'm still going to run out of room anyways. 5,000 times 0.04 all over 8.5 times 10 to the -7th. And since I know all my units are good, I can plug that in without writing down those units there. My maximum normal stress that this can handle is 340 megapascals. 340 megapascals. Right, much lower than the yield stress. So technically, even though it could technically handle this yield stress of 500 megapascals, we want to reduce our allowable to be this 340 megapascals so that it doesn't fail at those stress concentrations around the fillets there.